All right, today we're going to go over 6.3, which is polar coordinates. So let's take a look at the current system that we use to visualize functions graphically, and that's the Cartesian coordinate system. It's sometimes called rectangular coordinates. And so the way it works is, all right, let's say that there's a party at this point, and I was going to give you directions to that party. I would tell you the directions to the party are at 3, 4. And we all understand, since we've been working in Cartesian for so long, that means starting at the origin, I need to go horizontally 3 in the positive direction, and then 4 in the vertical direction to arrive at the party. And so that's our Cartesian system. So polar is a different system where instead I'm going to give you directions to the party, but instead of moving horizontally and vertically, I'm going to tell you a distance to go and an angle to go at, right? So we generally think of the angle as being measured from the positive x-axis here. So this is where we're starting our measurement, and a positive angle is measured counterclockwise. So I would say, hey, go to this angle, theta, and go a distance of r, and that'll get you to the same party. So we'll talk about how to convert from the Cartesian version, the 3, 4, into what r and theta should be, but we're going to establish a little vocabulary first. All right, so the polar coordinate system, we start with a fixed point O. We call that the pole. This is where we're measuring from. So this tends to be the origin when we are kind of setting up on our familiar Cartesian plane. The directed distance r to the point we're trying to get to, we can think of that as a radius, or sometimes it's referred to as a modulus. Okay. The axis that we measure from is called the polar axis, right? So that's, in general, for us, just going to be the positive x-axis. Okay. And remember that when we have a positive angle, we're going to think of rotating counterclockwise, and a negative angle, we will rotate clockwise. Okay. One anomaly I want to point out is you can also have the radius be negative. And so when you're graphing with a negative radius, so say this is the point where P has a positive radius, theta, and I want to graph a negative radius and the same angle. What I would do is rotate to this angle here. And when I normally would have gone in the positive direction, I'm going to go the same distance, but in the opposite direction. So it would make a straight line. And that would be the point negative r comma theta. And we'll see some examples of that. All right, so let's do an example. Just practice plotting some polar coordinates. This is called a polar plane, and it just has concentric circles. Each one represents one unit, and it just makes it a little easier to plot polar coordinates. So I'll show you why that is. Okay, so we want to go to pi over 3. We're going to plot the point 2, comma pi over 3. This is a little bit backwards of the way we're used to doing things, because when we look at Cartesian coordinates, we take the x coordinate, which is the first one, go horizontally and then vertically in the y direction. Here, we're really starting with the angle. So I'm always starting from this positive x-axis here, this guy here. And from there, I'm measuring off my angle. And then once I have my angle, I'll measure off my radius, right? So from the positive x-axis, we'll measure off an angle of pi over 3. Well, that's pretty close to pi over 2. It's in this direction. All right, and now I want to go out a distance of 2 units. So I'm going to go to the second concentric circle, and there is the point 2 comma pi over 3. Okay, that dashed line doesn't really exist. That's just, I'm showing how to count off the radius. So we're really just graphing a single point in the coordinate plane. All right, second one, let's use a different color. We're going to 3 negative pi over 6. So since we're measuring in the negative direction, we're going to measure clockwise from the positive x-axis. So negative pi over 6, right about here. And then we're going to go out a distance of 3. So there is the point 3 negative pi over 6. Okay. All right. And finally, 3 11 pi over 6. So now 11 pi over 6, again, measuring from the positive x-axis. This is a positive direction, so it's counterclockwise, and we're going almost 2 pi. 11 pi over 6 is pretty close to 2 pi, so we're going to go way around to almost here. We're going to go out to 3. There we go. There's the point 3 11 pi over 6. So note that this is actually the same place in the coordinate plane as this one. That's because, whereas in Cartesian coordinates, each coordinate represents its own place in space, right? There's no other representation of this point here, 3, 4, other than 3, 4. In polar coordinates, since it's rotational, we can actually represent the same point in space, i.e. this one and this one, same point in space, using multiple different representations. Okay, so think of this one as the shortest route to the party, and this one, we took the scenic route. We took the long way to the party, but we ended up at the same place. All right, so let's do an example where I want multiple representation of the same point. I want to find 3 additional points of this point, and they have to be between negative 2 pi and positive 2 pi. So let's graph the original point, 3 negative 3 pi over 4. So since we have a negative angle, we're going to be measuring clockwise rather. And 3 pi over 4, it's going to be past the first quadrant. It's going to be exactly halfway into the second quadrant. So right here. And then our radius is positive 3. So here we go. There's our point. Now we want to think of 3 other ways to get there. And they need to be between, our angle needs to be between negative 2 pi and positive 2 pi. So one way is just to measure that same angle, but in the positive direction, right? So if I go that direction, we can go look at our unit circle and note that if we go around, that angle was here. That's actually positive 5 pi over 4, right? Okay. So one way to do it is just rotate that way, and then my angle changes to 5 pi over 4. So radius is going to remain the same. So 3 comma 5 pi over 4, that gets me to the same party. Okay. Another way to do it is I could just rotate to exactly this angle across from it, but then make my radius negative, which tells me to go in the opposite direction. Well, notice that makes a straight line. So the way to figure out what that angle should be is just go ahead and add pi to that. So if I do pi plus negative 3 pi over 4, that's just going to leave me with pi over 4. All right, so if I make my angle positive pi over 4, but I make my radius negative, that is going to tell me to go in the opposite direction. So negative 3 comma pi over 4 will still get me to this same place right here. All right, and the last thing we do to keep it between negative 2 pi and 2 pi, I'm going to rotate from here all the way around to that green little segment. And then I'm going to make my radius negative again. So my radius is going to be negative 3, but my angle, we can look at our unit circle for this. If I rotate in this direction all the way around to here, right? That's in the negative direction. So think about where that would be in the positive direction. That would be 7 pi over 4 here. But we're going in the opposite direction. So that's going to be negative 7 pi over 4. All right. So we have 3 comma negative 7 pi over 4. And those all get us to that exact same point in space right here. All right, so let's see how to convert between Cartesian and polar coordinates. And to do that, we're just going to lay the polar system over the Cartesian system. So we've got our XY axis here, right? And then I'm going to just have the pole be the origin, and the positive x-axis is our polar axis. So that's where we're measuring our angle from. All right, so we got this point right here, which would be xy in our Cartesian coordinate system, right? Telling us if we want to come to this party, go horizontally x units, go vertically y units. And the same location would be r theta in polar. So go rotate a positive angle, in this case of theta. And from our pole, go a distance of r, and that gets us to the same place. And so what we notice is we get this familiar, what we call the Roxy triangle, right? And that's a right triangle. And so if we think of, for example, cosine of theta, cosine would be the adjacent side, which is x, over the hypotenuse, which is r, so x over r. And if I wanted to isolate x, I could just multiply both sides by r, and I get x equals r times cosine theta, right? And then likewise, sine theta would be y over r multiplied by r, and we get y equals r sine theta. And then, so that's to get from polar to rectangular. To get from rectangular to polar, we can note that tangent theta is y over x, opposite over adjacent. And then I can use my calculator just to do arctan to solve for theta. And finally, to solve for r, we have this right triangle. So we just use the Pythagorean theorem to relate r, x, and y, such that r squared is x squared plus y squared. Okay, let's go ahead and do an example of converting between each. All right, so we'll start with converting a polar coordinate to a rectangular coordinate. So here we're given a polar coordinate where our r is root 3, and our theta is pi over 6. So if I were to graph this on this polar graph paper, root 3 is a little more than 1. Pi over 6 is, say, right here. And so we'll put that point right there. Okay. If I want to convert to rectangular coordinates, I'm going to use x equals r cosine theta. And so x in this case is going to be our radius, which is root 3 times cosine of pi over 6. Go to our unit circle to evaluate what cosine of pi over 6 is. There we go. Cosine of pi over 6 is root 3 over 2. So we have root 3 times root 3 over 2. Root 3 times root 3 is just 3. So we get an x coordinate of 3 over 2, or 1.5. All right, to get our y coordinate, we get y equals r sine theta, which y is root 3 times sine pi over 6. Again, let's go to our unit circle. Sine pi over 6 is 1/2. So I get root 3 times 1/2, which is just root 3 over 2. All right. So if we think of this as the Cartesian plane, it tells us to go about 1.5 out. So here's 1. Here's about 1/2. And then go up root 3 over 2. Well, I said root 3 is a little bit more than 1. So this is a little bit more than 1/2 to get up to here. Okay, so let's go the other direction here. We're going to take our rectangular coordinate and convert it to polar form. And so we got the point 1, -1, or sorry, -1, 1. We'll zoom in a little bit here. And -1, 1 would be right here, right? All right. So all we're going to do is take this and make a triangle. All right. Note that this is -1, this is 1. So to find r, we can say r squared is -1 squared plus 1 squared. So r squared is 1 plus 1, which is 2. So r is root 2. Okay, so that's our distance from the pole. Essentially, this distance here is root 2. Now, the other thing we want to find is what is this angle? Theta. So we know that tangent of theta is y over x. So that's 1 over -1, which is just -1. So we want to figure out what value of theta that's in the second quadrant gives us a tangent value of -1. So if I go to my trig sheet, just clear this page out. All right, so we know we're in the second quadrant. We also know that, remember, tangent is sine over cosine, so it's y over x. So for in the second quadrant, for tangent to be y over x, we need them to have the same value but opposite signs. Happens right here, right? So 3 pi over 4. My theta is 3 pi over 4. So finally, my equivalent polar form of this equation is going to be r, which is root 2, theta, which is 3 pi over 4. And that gets us to the same party. Okay, last thing I wanted to show you is just a couple of polar equations. Polar functions, we're not going to get too deep into the weeds on this. I just want to expose you to it, are written in the form r equals f of theta. Okay. I'm just going to show you the two extreme cases. If I just have an r, if it's just r equals 2, then that means theta can be any value. So basically, we're just going out to a distance of 2, a radius of 2, right here. And since theta can be any value, I'm just going to trace out every point at a radius of 2. Boom, what we get is a circle of radius 2. All right. What about the opposite? What if it's theta equals a constant? And this is kind of the y equals a constant and x equals a constant in the coordinate plane situation, right? If y equals a constant, we get a horizontal line. X equals a constant, we get a vertical line. So in polar form, if r equals a constant, we get a circle. If theta equals a constant, we're going to go to that angle. So pi over 3, I'm going to say that's right about here. And r can be any value. So if r is positive, it's going to be every point along this line in the positive direction. But remember, if r is negative, we go in the opposite direction. So it's going to be every point along that same line in the opposite direction. So what I end up with is a straight line. All right. That's it. Go ahead and get started on your group work and the delta math.